So this is a classic example of a Faraday's law problem. If we take these two loops of wire and we let them drop down the page under the influence of gravity, we'll have a changing magnetic field in both of these, or a changing magnetic flux through both of these. There'll be an induced EMF in both of these, and so there should be some backwards force experienced by both of them. The question is which one falls further, so which one experiences the larger backwards force will fall slower, so the one that experiences the smaller backwards force falls faster. In order to actually do this, we can use Faraday's law, which is the integral, loop integral, dl dot E, right, is equal to minus the time derivative of the magnetic flux, d2x in hat dot B. Well, I can see that the change in the magnetic flux here is going to be twice as big because this loop has twice as much size this way. It wouldn't matter how big it is up and down. It only matters its size this way because it's falling down. So the change in flux will be twice as big, and so its EMF will be twice as big. Well, if its EMF is twice as big, then the current through here will be twice as big. Will actually be the same size. Sorry. So the current is going to be the same size because I have twice the rate resistance. So the EMF is twice as big, but with twice the resistance, using the fact that EMF is equal to current times the resistance. If EMF is twice as big and R is twice as big, the current's going to be the same size. So I'm going to have the same current flowing through each one of these. When I have the current flowing through a magnetic field, I'm going to get a force that points up, okay, in both cases, and we know that just from Lenz's law that this is going to resist. The force, magnetic force, right, is proportional, to the current times the length times the size of the magnetic field. The current's the same, the size of the magnetic field is the same. This one will have a magnetic force that is twice as large. So F mag is going to be twice as large than here. So I'm going to have a smaller magnetic force here than here. Assuming that they have roughly the same masses, and so actually it gets a little bit complicated here. I didn't give you quite enough information. Assuming they have the same masses, this guy is going to fall faster because he has a smaller. If this, because its loop is twice as big, has twice the mass, then they will fall at the same speed, right? Because the force times the divided by the mass is the acceleration, and so they'll fall at the same speed. If this one you consider as being a big area, if this one scaled as 4 times the mass than that one, because maybe you had to put paper or something to hold it, and so the area scaled, this one would actually fall faster than that one. So it depends on the mass distribution. Again, assuming they're equal masses, which would make sense to me, because I think the mass would be dominated by the resistor as opposed to the wire, and the resistors are probably going to be about equivalent masses. If they're equal masses, okay, if they are equal masses, then the smaller loop will fall faster. Smaller loop falls faster. There you go.